Welcome to Java Foundations Section 2.3, Introduction to Object-Oriented Programming Concepts. In this lesson, we'll explore how Java models real-world objects in code. In this section, we'll discuss major elements of object-oriented programming and how it is different from procedural programming. We'll also discuss what a class is required before an object is created. Let's reflect for a moment. After all the computing power and clever code we've built, a cat. That playful moment reminds us programming starts small but grows powerful. Of course, Java can do much more. It's time to explore how it supports modern programming styles like object-oriented programming. Procedural languages like C can run line by line with specific sequences. Object-oriented programming language like Java model objects and allow for more flexible interaction between parts. The diagram illustrates how object-oriented programming stresses the interaction of objects. Let's try a hands-on activity. Play Java Puzzle Ball levels 1 to 5. Observe what kinds of objects are on the field and how placing walls on bumpers changes the gameplay. By the way, you're welcome to play Beyond Basics Puzzle 5. Puzzles beyond Basic 5 are associated with later sections. As you play, think like a programmer. Each object you see has a role, and how it behaves matters. We'll tie this back to Java's object-oriented concepts soon. What objects did you notice in the puzzle game? Maybe bumpers, a ball, duke, or level geometry. These are all models in code as objects. In object-oriented programming, objects don't run in a strict order. They interact dynamically, just like in our puzzle game. Try placing a triangle wall on a blue bumper. Notice how every instance of blue bumper behaves the same. That's because they share the same class blueprint. A blue bumper is an object, and every instance of these objects will share the same behavior when interacting with the ball. These behaviors may include deflection via the triangle or the simple wall. Let's describe one of these blue bumpers. It has properties like color and position, and behaviors like flashing or making a sound. These are modeled in a code. The ball is also an object with its own properties and behaviors. It moves, changes direction, and reacts when hitting other objects. When a blue bumper and a ball interact, the bumper triggers actions like flashing and sound, and the ball changes direction and updates its position. All blue bumpers share the ability to ping, flash, and interact with the ball. So, why does all this matter? Because you've just seen core principles of object-oriented programming. What are those? Shared behavior, interaction, and object properties. Let's switch examples. A cat object might have properties like name, age, or breed, and behaviors like mewing, playing, or hunting. Notice the subtle difference between favorite food, which is a description, and eat, which is a verb. In Java, we model cats or any other object with a class. A class is the blueprint. We can use it to create many instances of similar objects. Here we've created 3 cat instances: Open, Tiger, and Misty. Each has different values for the same set of properties, but they all follow the same structure. Now, think about programming strategy. When you have an idea, identify the objects you need, their properties, behaviors, and how they will interact with each other. Now, when you design a Java program, first identify the objects, then determine the object's characteristics or properties, and then determine the object's behaviors or operations. It's also useful to consider how objects will interact or affect each other's properties. The final step is to translate that analysis into Java code to create your application. We show this final step toward the end of this lesson to show that it's possible. You won't be asked to write your own code for a Java class until later sections. Objects aren't always physical. They can be conceptual, like an online account. What matters is that each object has properties and behaviors you can describe in code. To validate objects in a problem domain, such as the Duke's choice order process, you identify the properties of all objects. Objects can be physical or conceptual. A shirt is an example of a physical object. A customer's credit card account is an example of a conceptual object, but it isn't something you can physically touch. Objects have properties or attributes such as size, name, and shape that represent the state of the object. For example, a person has a name, Mrs. Duke, and an object might have a color property. The value of all of an object's properties is often referred to as the object's current state. An object might have a color property with a value of red and a size property with a value of large. Objects also have behaviors, such as things they can do, such as, in our example, shop, put an item in the cart, and purchase. A reminder, a class is a recipe. It defines the structure of an object. From that class, you can create many object instances. We just discussed some of the object's characteristics and behaviors in the Duke's choice scenario. Here is an example of one of Duke's choice objects, the customer, and its function in the store. Customer is the class, and the class is the blueprint or recipe for an object. The class describes an object's properties and behaviors. You use classes to create object instances, such as the 3 customer object instances, as illustrated by the 3 images. Now try this. Design a coin sorting machine. What objects would you need? Maybe coins, a sorter, a counter, and a printer for receipts. Pick one of these objects. What are its properties? What behaviors does it need? This is how we model objects in Java. Let's walk through a customer example. Properties might include name, age, and order number. Behaviors could include shopping, adding to a cart, or setting an address. Think of some properties and behaviors that are in the customer class of Duke's choice. Think about how you would write this information as a Java class. Now, see how we translate that into Java syntax. Each property becomes a variable, and behaviors become methods inside the class. Now we're beginning to see the transition to Java syntax. Here is the complete class in Java. You define the fields, then add methods to describe what the object can do. In the previous slide, we identified some properties and behaviors that might be in the customer class. This, for example, demonstrates how the properties and methods are created in Java. Here are the basic components of a Java class. Class declaration. Notice that the entire class is surrounded by curly braces. Fields of a class. These fields represent the properties or attributes of the class. Methods of the class. These methods represent the behaviors or operations. Here we see just one method, display customer. Note, in the code example, the word public is a modifier. You'll learn about modifiers later in the course. This class is a full model of the customer object. It holds everything we need to store and act upon in a program. As you design an application, it's often helpful to create a simple model that describes the components of a class. In the table, the class name is listed at the top, the properties or fields are listed in the second row, and the behaviors or the methods are listed in the third row. If you compare this modeling in terms of language, think of the class as a noun, the properties or fields as adjectives, and the behaviors or methods as verbs. In Java, we use the term fields for data properties. These are also known as attributes or data members. Section 3 will explore data even further. To summarize, object-oriented programming allows us to model the world with classes and objects. Each object has properties and behaviors, and they interact in flexible ways.